Hello, my name is John Mazzie. I'm a member of the technical staff at Micron Technology, and today I am going to be talking about application analysis that we do through the NVMe driver using BPF. The first thing I'm going to talk about is BPF and how we use it to trace the NVMe driver. And then I'm also going to do an application analysis, and the application we chose is MLPerf storage to analyze for this because we will, that way there's a good example, and this is a benchmark for testing storage for AI training workloads. So just a brief background on BPF, if anyone that isn't familiar. It was originally developed as the Berkeley packet filter, and it was developed to analyze network traffic. It is now integrated with the kernel, and it's used to execute sandbox programs which trace and profile either trace points or kernel functions within the kernel. Different features have been added over time, so depending on what features you need out of BPF, you may be required to use a newer kernel or have to do things in the harder way if you're not using newer kernels. One element of BPF that is conceptually hard to get around is like inside a BPF function, you are limited to 512 bytes of memory. But the way to work around this is to actually use like a memory map. So these memory maps are memory blocks that you allocate, and then you can share these memories between your different trace handlers, and then that will allow you to store more than this 512 bytes of memory. So one of the, there's a few different things you can trace within the kernel, and this is not an exhaustive list, but one is trace points. Trace points are specifically implemented within the kernel to allow this tracing to grab data out of a function. So they're placed within specific given functions, and they have a stable interface across multiple kernel versions. So if you're using trace points and you want to trace data with different kernel versions where the kernel may have changed, this is your best bet for having a consistent API. Another way is you can just trace the K-probes, which are the kernel probe, on a given function within the kernel. Because the API in the kernel can change from version to version, these are not stable. So sometimes if you develop a tool with a specific K-probe on a specific function, it will not work across multiple kernel versions. So you may have to develop either multiple versions of the tool or other ways to trace with multiple versions. And then there is BPF trampoline, which is the kernel function and the kernel return function. And these are very similar to K-probes. The interface is the same. You're still tracing the same kernel probes, but there is reduced overhead with this. And it's a newer feature in one of the newer kernels. I believe it was 5.5. One of the other benefits of this is, and this is, we ended up going down this route, is because since we're tracing two different functions within the NVMe driver, trace points and K-probes can both miss functions, can miss traces if they're interrupted. So while you're doing submissions on the in the kernel driver, you could have completions come in where an interrupt starts to do the completion, so you trigger your second handler, but the second handler can't run using those two interfaces. So you end up missing completions on your driver, so, or on your traces. So if you actually want to see every single transaction on a driver, going through the driver, we found that you need to use the BPF trampoline. When we first started developing tools to trace the NVMe, or to trace applications, we first started with block trace, which is built-in Linux tool. It's easy to use. It traces at the block driver, but then does require post-processing near the end. And then we used another BPF based tool, and it used BPF trace. which is a high-level scripting language that interfaces with BPF, and this was NVMe lat. It used trace points, so that's one of the reasons why it could miss the transactions, and it only gave us like a latency histogram of transactions because we were interested in latency at first. With the new tool that we have, we do the data processing in line. So for every transaction, we end up collecting the starting time, the stop time, latency, starting LBA, the length, and other stats like that. And this is for every single transaction. And this gets output through to a file in a normal like CSV format that's pretty easy to look at and parse. They can get very big depending on how long your test is and how many IOPS you're actually performing over that test. And this just is a basic block diagram for the Linux storage stack. So it just has a couple of points where it shows where traces are happening. So you can see block trace there traces the block layer, and NVMe trace is tracing at the driver layer, which is our NVMe driver in this case. So here is the information that we actually collect with the NVMe trace tool. It shows the starting LBA, size, length, times. We also grab the process ID that is triggering the specific transaction, with the name of the device, which NVMe queue it's going, what kind of transaction type. And we developed using libbpf, which is a library that is, it's a C library that interacts directly with the BPF layer. There's a few other libraries like BCC. It seems like most things are moving towards using libbpf. There's also the BPF trace, which is a high-level scripting language that you use it at the high level, and then it will use BCC and libbpf to actually generate its code that it's interacting with BPF. But we decided to use libbpf because it gave us more control over all the little things that we wanted to do, much easier. And this is why we use libbpf. And then another benefit with libbpf is there's this concept of compile once, run anywhere. And they do this through multiple helper functions that when the BPF code is running, it gets compiled right at the actual BPF instructions get compiled right as you're executing. So the very first thing that it does, it will find structures and get the memory offsets for specific parameters that you are accessing, so that even if the kernel has changed a bit, you will still get the correct data. And it does these through these helper functions, which will do memory reads and be able to determine where things are in the kernel based on the specific kernel version. The code flow is basically in the kernel space, we have memory maps. So that's where you store the data in the program while it's being processed. And then in order to actually map everything, we use a per CPU memory map. So each CPU is not trying to access the same memory map at the same time. And then we use a ring buffer to transfer data out to user space. So all of this BPF code at the handler level is actually be running in kernel space. And then you use user space code to take the data from the ring buffer and output it to files that the user would need. We use 3 handlers to trace our transactions. One is the NVMe submit command. So this is the kernel function that actually submits the commands to the NVMe device queue. Another is the NVMe setup discard. And this is where the discard commands actually get set up within the kernel. And the reason we need to look at that is because discards, you can send multiple at the same time using a single DSM command. So I think a DSM command can support up to 256 discard commands in a single NVMe command. And so this way we can see all of the individual discards going to the drive. And then we do NVMe complete request, which handles the completions of transactions when the interrupt is activated. So, and this is where we get the end time. Most of the rest of the data comes from the NVMe submit command. And then in user space, we load the BPF application, and then we handle the data processed from the kernel space. One of the important structures that we need to look at is the request and command structures. So in the request structure, it's the structure that contains data from the block layer that is provided to the NVMe driver. So from this structure, the NVMe driver sets up the NVMe command going to the drive. And then we have the NVMe IO data structure. And then in memory, this exists immediately after the block request. And then it contains a structure for the NVMe request, the NVMe command, and the NVMe queue. Because every kernel function does not have every structure passed into it, a lot of times you pass one structure and then you'll jump around in memory to get to the other structures. The tool needs to access these, so it limits direct access and readability of code in different kernel versions because these functions do change to some degree. Like going to, I think it was Linux kernel 517, the NVMe submit command gets kind of displaced by the NVMe submit commands. So it submits multiple commands to the queue at the same time. But this new function, by default, isn't actually traceable. The symbol's not exported. So you can't always trace every function unless you recompile the kernel in the way that you need to trace specific functions. And then getting data from the NVMe IO data and the requests then requires moving around memory. So jumping between structures, you need to know the specifics, and this is where the BPF core code comes in to help with structure changes between kernel versions. This is just the NVMe setup discard handler. One of the things that's difficult in BPF is loops. In BPF, loops have to have a defined end. You cannot, and it has to be clearly defined because the compiler, when it checks, if it even thinks that you could change the index value at any point in the loop, it will immediately tell you it's not valid, even if you know in your code it never changes. So sometimes you have to do a little bit of work around to make sure it knows, hey, this loop ends in at most 256, because this is the discard command. In newer kernels, there's a helper function to make it easier to do loops in BPF, but because we're on an older kernel version, we didn't actually have access to that. And then, yet again, the discards are sent through the dataset management command, and there can be up to 256 per one of those commands. On the NVMe submit command, this is where we generate pointers necessary for the location of structures. We check, and then we use a memory map as a heap in order to get around the 512 byte limit. So with all the data we're collecting, it ends up being more than 512 bytes per transaction. So, 512. Couldn't remember if it's 512K or 512 bytes. So we use a memory map that acts as a heap. So it basically has a single structure in memory per CPU that you can use as an interim place to hold your data as you store the transactions to handle at the completion while you're collecting the data. And then in the submit command, we collect available data. We can check if it's an admin command or a standard transaction command. And then we store this information in an event map, and then we look it up when we get to the completion handler to match up with the submission, so we collect the rest of the data. And then in the completion handler, we get the matching information from the request, and then we reserve space on the ring buffer we calculate the latency, and then we write all the collected data for the transactions into user space using the ring buffer. And this is just an example output of the tool. And you can see it's just a standard CSV file with a header at the top. And we have the start times, end times, latencies, process names, process ID, device, QID, starting LBA, length in bytes, and length in LBAs. And one of the reasons we collect both length in bytes and length in LBAs is that when you get these transactions, it does not tell you what format the drive was, what LBA format the drive is using. But if we get both lengths in bytes and length in LBAs, we can calculate the original LBA format of the drive. Here's just some examples of the BPF helpers functions that we use. So how we get the current time for latency is just BPF kernel time, get in nanoseconds. The next couple functions give us the process and the process ID of the triggered event. And then BPF core read, BPF probe read kernel, and BPF read string. These are BPF helper functions that let you read arbitrary memory locations or read specific things from structures that within BPF code. You can do them using your own pointers, but these do a good job of helping you when you're running on different kernels because it will reallocate, it knows how to reallocate each structure. And then the big benefit of libbpf and BPF core is that the compile once run anywhere, so you can develop your tool to run on multiple versions of the kernel. Though, when the actual API changes, it is a little bit more difficult to do this, whereas if the multiple versions you're running on are similar or have the same kernel APIs and just structures slightly change, it's a lot easier to do these things. So I'm going to go through one application analysis with MLPerf storage that we did using our tool. I'm going to start by just briefly describing what MLPerf storage is. MLPerf is a consortium, and it's built around sizing and doing AI training. But there's the MLPerf storage specifically. So doing these AI trainings is difficult for a storage company because typically we don't have a lot of GPUs to do real training. So one of the ways the MLPerf consortium is working on this is to use the MLPerf storage benchmark. It uses a tool, DLIO, from Argonne Leadership Computing Facility. And this uses the same data loaders as a real workload would. So like if you were doing UNet3D or BERT or something like that, you would actually use like PyTorch or TensorFlow or something like that to access your data. What DLIO does is uses these same data loaders so you get what the real workload will work like. Even if you don't actually do training, we're just emulating the storage access from our storage perspective. And the way it emulates the training is it basically just has some sleep times and specific parameters to just emulate what's happening when basically pausing the workload to storage while training actually occurs. Right now, there's only 2 workloads defined in MLPerf storage. One is BERT, which is a natural language processing, and UNet3D, which is a 3D medical image processing. The workload we're going to look at is UNet3D because BERT doesn't actually stress storage very much. The transactions are very small. It's not a very tough workload for storage to do. UNet3D, because the images are very big, it shows more of a difference in how different drives will perform, at least in that workload. So in this first chart, this is a bandwidth plot for 2 different runs of MLPerf using UNet 3D. The top one is where we emulate one accelerator. So this would be just one GPU running against a single drive doing UNet 3D. There's 5 different peaks because there are 5 different training epochs as part of this test. So at the beginning, you get these very high peaks because it's going to prefetch data to fill up your GPU. And then you're going to be, after that, and you start training, you're going to be pulling more data in as images get processed. And then below, we have an example for 15 accelerators. So you don't see as many peaks because, and this is still just testing against one drive. But you can see that the throughput significantly changed between one accelerator and 15 accelerators. So with one accelerator, the max throughput was about 1,500 megabytes a second. And with 15 accelerators, your max throughput ends up being around 6,500 megabytes a second, which is the limit that this drive could actually perform at, or very close to it. And then on average, you would see 5,700 megabytes per second. But the thing you can see here is that frequently, and this is all 1 second interval averages, you can still see lots of time where the drive is not at max throughput. You can see lots of stuff down near 0 or even below 1,000 megabytes per second. So this is another thing we can look at is the queue depth over time of the drive. So with one accelerator, the drive never actually gets above 10 queue depth. And the way we determine this is basically just looking at start times and end times of transactions and doing a calculation to see what the queue depth is at any given transaction. So we calculate that for every transaction in the log, and as things complete, we reduce it. As things start, then we increase it. And then with 15 accelerators, you actually see the queue depth on the drive goes, on average, it's about 120, but you see some peaks up to about 145, which is a much higher queue depth. But it doesn't tell the whole story. So even though it goes up to 10 queue depth and up to 120 queue depth, this is the one accelerator test. So this is a different view of the queue depth, and it actually shows by percentage how many transactions are ever at a specific queue depth. So close to 50% are actually at QD0, which means it's the initial transaction on the queue. And then the other almost another 50% are at QD1, which means it's the second transaction on the queue. And then even though it gets up to 10, a very small percentage of the transactions actually are at that high queue depth. So with a single accelerator, the drive is idle a lot of the time. It's almost always waiting for a transaction. It's more interesting at 15 accelerators. So you actually get this peak that's between like 70 and 110 queue depth. So most of the time it is being used, but then you also see this small peak down here between like 0 and 10. And that adds up to about 5% of the transactions. So even with 15 accelerators against one drive, you still have some of the time it being close to idle. And this just shows that like real world workloads are not always driving your drive fully all the time. It's very hard to do that. So a lot of workloads do have this idle time in. And then, and we're also going to we can also look at like how different device settings can affect the I/O pattern. So 2 of the device settings we're looking at here is maximum data transfer size. It's a controller setting. It is the maximum transfer size the drive will accept, reads or writes. It can be adjusted within the kernel setting can be adjusted just running in the OS without having to reboot the device. But it can only ever be lowered down. It can never be set above what the drive's MDTS is actually set at. And then you have the namespace optimal right size. which can't be adjusted in the OS. And it's really just a hint. It's not required. It's just saying, hey, if you want the best out of me, try to do this. And here's a comparison of like how a block size pattern for the exact same workload can change based on these settings. And this is because during this test, we're actually using a file system, and the file system uses these parameters to try to figure out how best to set up its structures for the device. So even though the workload from the benchmark is exactly the same across all of these tests, you can end up with different I/O patterns just based on what you're telling the Linux system you should do. And this is just a difference between a 4 megabyte MDTS and a 4K now setting. Most transactions are around 128K with those. And then if you change just the now setting to 256K, most transactions actually end up going towards 512. And it's hard to see because the red dot is right behind that little read legend at the very top. And then if you just adjust MDTS down to 512, which you'd think wouldn't change anything because it only maxed at 512, you actually get a more even distribution for these, for the I/O pattern, where the average is around 256, but none of them really peak up above the others. There are some things we would like to do in this version and in other versions of the tool. We would like to trace like the exact file that's accessed by a transaction, and then trace the application processes and improve the analysis. And also like trace all the way up to the application down to the down to what's happening on the drive. That way you just get a full picture of what the application's doing. And then, are there any questions?
Yeah. So this one is from the moment there's no way to actually tell the Q to D latency, right?
Say that again, I'm sorry.
From the time the I/O is queued to the time it hits the driver, there's no way to tell that latency, right?
Yeah, so with this tool, because there's no place that we can measure between the submit function and when it actually gets it. The only way to really do that is with a PCIe bus analyzer. The question was, is there a way to measure?
You can do it with vtrace, log trace.
Okay.
Log trace, you can actually tell the time where the I/O was added, inserted, queued, from the time it's queued, right? All the way down until it hits the driver, and then you get the completion.
Yeah, so it looks at where it gets to the driver, correct?
Yeah.
So I'm measuring at the driver, so I'm already measuring at that lowest level. I could measure from a higher point to get that, yes.
Yeah, if you do that, because you could get artificial high D2C latency due to high Q2D latency. Because of like system issues or whatever.
Yeah.
So if you are able to include everything like block trace, then this is a better tool because of the scripting language and everything you've done here. So
yeah, and that's one of the reasons why we ended up making this tool, is so we could reduce, since we're a drive vendor, we cared more about what was happening on the drive and didn't care as much about what was happening on the system. Now we're getting to the point where we need to care about that, because then we can help our customers like understand, hey, something's happening on the system here, because we can measure that.
Yeah, and also because it could end up artificially inflating that D2C number.
Yep.
Because the system is not really able to submit the I/O to the drive fast enough. Thank you for the presentation, very nice.
Yeah, thanks. Steve?
So, you made this about the tool, but you showed us some perf data that said a single SSD can feed $50,000 accelerators. Did you possibly answer the question, does storage gating AI, or is it a function of the workload specifically?
It's a function of the work. So the question was, did I prove that storage doesn't really, like, you can just use a little bit of storage for a lot of an AI workload? And the answer is, it depends on the AI workload. Since this is just pulling the data from the drive and then filling it up in memory, because a lot of time is still spent on training, it's not trying to access the drive all the time. It's just trying to read data as fast as it, get it into memory, and then do the training. And then as it finishes, it will go and grab some more. And because the training takes time, you don't need the full utilization of a drive. Now, for something like memory replacement, where you're trying to do like the actual training using storage as memory, it's not going to be able to saturate 15 accelerators. You're going to need like multiple devices, 4 to 8, to saturate your accelerator, because it's constantly going to be reading and writing because it's using that as memory for training. Yeah, that's true. Another question back there?
Yeah, so I think my question was related to this, but so in those two benchmarks, what is the size of the address space that you're accessing? Like in the one accelerator, 50, is it like it's a 1 terabyte drive and you're using an 8?
Yeah, so
you're spanning the whole space?
This was an 8 terabyte drive, and the data set is 1.3 terabytes. So we want to make sure that the data set was bigger than system memory in the test, but we didn't necessarily care if it was the full drive for the test.
But in the 15 accelerator, it's not 15 times larger.
It's not 15 times larger. It's the same data set with just 15 accelerators. And one of the things you can see is that actually in the 1 accelerator test, it takes 1,600 seconds to finish the training. In the 15 accelerator test, it takes around close to 1,200 seconds. So it's significantly faster with more accelerators. But that's the training part. It's not, because it's not really an effect of the drive, except that the drive can support up to 15 accelerators. Another question?
Does running this tool cause any measurable performance impact?
It does. It's small, and since we're not worried about like getting the full, we're trying to understand the application so we can help design the drives going forward to see what kind of workload patterns do we need to recognize, what kind of things do real applications do. It's not just 4 corners FIO where you do sequential reads, sequential writes, some random 4K, and some mixed. So it does, but it's a very small, and that's one of the reasons why we use libbpf, because it has less of an effect on the performance. But yes, there is a performance hit to running the tool, but it is small. And then I saw another hand somewhere. Yeah, I think it's single-digit percentage. I don't know exactly off the top of my head, but I'm guessing less than 5%. Yeah.
I have a follow-up question to Steven's question. It's not about the tool.
Okay,
also,
that's fine.
But would the AI use that, okay, memory, so if you do something like memory semantic drive or something like that, then you would see more of like 10 drive, 8 drives you said, to saturate a single accelerator GPU. Do you know like what would be the read-write ratio in that case?
I'm not actually sure off the top of my head. I know NVIDIA had a paper about, it's called Big Accelerator Memory, and that's a code base we're looking at to do that, and it uses the drives essentially as memory replacement, because their goal is to reduce total cost of ownership. So you don't need a ton of system memory. You just need enough drives to be able to saturate the transactions. So in that case, you're not necessarily saturating the bandwidth of an individual drive. You just need to saturate the transactions to it, because you're essentially, the GPU is just going to read and write as fast as it can. So you need a lot of drives because it can do a lot of transactions really fast.
Training usually just read, or?
For this, it would be mostly read, because you're just reading the data. Yeah, and then for BAM, it's going to be a mix, because it's actually storing the active training data set. So it's the features and things will be on the drive. So you'll be reading and writing. But I don't know what the mixed percentage is of that.
Thank you.
Yep. One more question. No, you're fine.
Are you storing the traces on another drive?
Yeah, so when we do our trace, we put another drive in the system to Yeah, because they can get pretty big, especially if you do a longer test. So the drives are gigabytes in magnitude, but we've done longer tests where we've had 100 gigabyte file before compression.
So you know, in terms of overhead, you know that like one log drive can handle half a dozen or something data drives. Like you wouldn't have to have, if you have 6 drives that you're measuring, you don't have to have 6 drives.
Yes, that's true. Yeah. And then another question. Yep.
Any chance you'll release the code?
I would like to, but that's a negotiation I'm currently having with Micron. Because I think the tool would be, no, it's not all in there. The basics that pretty much anyone that would be interested in BPF to trace is in there, but I would like to release it as an open source tool because I think it would be better, because I'm not a developer. I'm not a C developer. I learned libbpf over a weekend because I was interested in it, and we needed a tool. But I think more experienced developers having access to the code, I could learn a lot. The industry would benefit from it, I think.
I should send him an email. Put in an email.
Yeah, I would love it.
Sorry, is the AI traces available on GitHub?
Sorry.
Unit 3D and the...
So MLPerf storage, I believe, is available on GitHub. So it'll have BERT and UNet, and I think it has instructions on how to run the tool.
Yeah, but is there any way the trace would be available so you can just replay?
Our trace wouldn't be, but the MLPerf storage, it's an open source tool, and it's
So you have to run it and then get your own trace?
Yeah, you'll have to run it to build the data set and then run it to get your own trace, yeah.
Thank you.
Mm-hmm. Well, thank you. Yeah. Okay, thank you very much.